Thanks to Brilliant for sponsoring today's video.
Today we're going to show how all of mathematics can be constructed from, well, nothing at all. That is, it's possible to start with simply the empty set and then perform set theoretic operations until you have all of the building blocks of modern mathematics. And of course, we're not going to construct all of modern mathematics. We're going to stop at maybe the rational numbers, because I think that's maybe far enough without maybe getting too far into the weeds to maybe prove the point that everything can be built out of nothing. Okay, so we need to recall a few things to get off the ground. The first is one of the axioms, or really it's a result of one of the axioms of Zermelo-Fraenkel set theory. And that follows from the axiom of union, or what I really mean is that what we need will follow from the so-called axiom of union. And that is that if you have two sets and you take their union, you get a new object which is also a set. Now, this may seem totally obvious, but in fact, we need an axiom for this to be possible. And then we're also going to recall something called the Peano axioms, which we did a previous video on. And that essentially says that the natural numbers are uniquely defined by a certain setup. And that is, they contain some number which we'll call 0. And then along with containing 0, there's a successor function. And that successor function is injective. So that means it's 1-to-1. Furthermore, 0 is not the successor of anything. So you want to think about this as the successor function takes a natural number to the next natural number. So -1 is not a natural number. Well, the successor of -1 would be 0, and so that's why we have this condition right here. And, well, like I said, we want to think about the successor function as being the next natural number. So in other words, it's n+1. So also the natural numbers not only have the ability to add 1, we should be able to add any two natural numbers and get a new natural number. That means it's a so-called maybe commutative monoid. And the way that we define addition more rigorously after this setup is by a recursive definition where we have m plus the successor of n is equal to the successor of m plus n. So, like I said, in that previous video, we looked at this kind of stuff. And in fact, in that previous video, we proved that this setup leads to an associative rule of addition and a commutative rule of addition. And I think in a forthcoming video, we'll look at how we can define multiplication out of these parts. But there's actually a question which we've left uncovered. And that is maybe based off the following, setup or the following question. So we've got some rules that would define n, but how do we know that this set of natural numbers exists in the first place? And this may seem like a totally obvious or maybe a totally silly question, but we could maybe come up with another definition of an object that seems kind of interesting. We could maybe call a super strange function a function that is differentiable but not continuous. Okay, so we've got this definition, this defining property of super strange functions. They are non-continuous, but they're differentiable. Oh, but via real analysis, or maybe basic calculus, you can prove that every differentiable function is continuous. So that means, well, there are no super strange functions. In other words, there does not exist a super strange function. So anytime you start maybe building some sort of definition or writing some axioms down for some mathematical object, it's always a good idea to make sure that type of mathematical object exists in the first place. And that's what we'll do here. we'll actually build a set theoretical model for the natural numbers. And then using that idea of the natural numbers, we'll build a model of the integers and then a model of the rational numbers. And since we'll see that we started at the empty set, we'll essentially show that the rational numbers are built out of only the empty set. Okay, so what do we need here? Well, we'll start with a 0. So if we're building this in the framework of set theory, what should we use for our 0 element? Well, I think this is not a trick question at all. There's kind of one obvious 0 element in set theory, and that would be, well, the empty set. So let's say that 0 will define that to be the empty set. So I'll use that notation for the empty set, but let's just recall that that is the set containing 0 elements. Oh, well, we've got a set containing 0 elements, which gives us the number 0. Well, perhaps a set containing 1 element should give us the number 1. Okay, well, all we can work with is the empty set. So how do we build a set containing 1 element out of the empty set? Oh, here's the way to do it. So we will define the number 1 to be the set containing the number 0. In other words, the set containing the empty set. So this may seem kind of silly. Isn't this just the empty set? Well, it's not. It's the set containing the empty set. So there's in fact 1 element in here. Okay, well, now we really need some sort of idea of how to define all of the natural numbers, and this gives us a clue. So since 1 has 1 element, perhaps 2 should have 2 elements. But what should those 2 elements be? Well, so far we've only got 2 different objects to work with. The number 0, which is the empty set, and the number 1, which is the set containing the empty set. So if we put those together into a set, well, then in fact we've got a set with 2 elements, and that sort of makes sense to play the role of the number 2. So we could write this as the set containing 0 and 1, but observe that is the set containing the empty set and the set containing the empty set. So I said that phrase, the set containing the empty set, a couple of times, but that being said, one was composed inside of the other. And now we can just keep going on and on and on. I think we see kind of a standard structure here. So perhaps we would define the number 3 to be the set containing 0, 1, and 2, because that's a set with 3 elements. Oh, but then we could write that in terms of our definitions. So that's the set containing the empty set, and the set containing the set containing the empty set, and, well, let's see. I'll just write it down and we can take a look at it. So there we have that. So let's just see that the number 0 is right here as the empty set. The number 1 is right here as the set containing the empty set. And then the number 2 is right there. Okay, good. And now, well, we could just keep going on and on and on. But I think what we would see is that the number n should be defined to be the set containing 0, 1, 2, up to n minus 1. And that's because, well, that's got n elements, and that follows this pattern that we have right here. And that gives us some sort of clear idea of how to define our successor function. In other words, our plus 1 function. So let's maybe observe that n plus 1 following this pattern is the set containing 0, 1, 2, up to n. Well, maybe let's put an n minus 1 in there so we can see that. Oh, but observe that that is simply the set previous union with the set previous. In other words, this is going to be equal to n union the set containing n. That's exactly what we have here. And that gives us some motivation for the following definition. So here we have our successor function s of n is defined to be in union the set containing n. And as you can see, that will rebuild all of these kind of things that we've been led to define already. So the successor of 0, well, that's going to be, well, let's write this down here. So let's notice 1 is equal to the successor of 0, which is equal to the empty set union the set containing the empty set, based off of this definition. But the empty set union anything is just, well, that anything. So here we get simply the set containing the empty set, which is our original definition. And you can see how this would work for the number 2 and so on and so forth. Okay, so this is the definition that we'll use for this successor function. But maybe before we move on, what I'd like to point out, well, is first of all, that the empty set is not in the image of this successor function. So I think that's pretty clear, because if we union, well, notice that first of all, this object right here, this set containing n, is always non-empty. So like I said, this thing is always non-empty. But that means that anything that's the output of our successor function is always non-empty, yet our number 0 is the empty set. That means we can never achieve the number 0. But let's also recall, or maybe let's also look over here and notice that we need an injective function, but I also think it's pretty clear to see that this is also an injective function. Okay, so there we have it. There's our set theoretic model for the natural numbers. But before we move on to the integers, I'd like to point out that there was an original definition for this successor function that Zermelo defined, but it wasn't really quite as good as this one. It, still built the natural numbers, but it was not extendable to infinite ordinals like this is. These are, in fact, an example of ordinal numbers. And Zermelo used the following definition for the successor function. S of n was simply the set containing n. So that would maybe give this alternative view. Maybe we'll look at the number 3. So in this setup, we would have the number 3 would be equal to the set containing, the set containing, the set containing the empty set. Okay, so notice that we're still kind of counting the number 3 appropriately based on how deeply composed within the set containing the empty set is. That being said, if we were to count the number of elements in the set that is defining 3, we would not get the number 3. So it's not quite as nice in that view. Okay, so that being said, well, we've got our set theoretic model of the natural numbers. Now let's build the natural numbers into the integers. And we're not going to need the set theoretic model of the natural numbers anymore because we've already built the natural numbers. Now we can use them, and anything that we build out of the natural numbers will be, built out of that set theoretic framework that we had. That being said, we will jump back and look at the set that is defining a certain integer, just to make sure we see what's going on. Okay, so let's get to the integers.
I'd like to take a minute to talk about today's sponsor, Brilliant.org. While watching my videos is a great place to start, you get more out of learning by doing. And that's why I highly recommend you sharpen your skills with Brilliant. Brilliant is where you learn by doing, with thousands of interactive lessons in math, data analysis, programming, and AI that are individually matched to your unique level. Each lesson comes with hands-on problem solving so you can truly learn the material. It's been proven to help you learn 6 times more effectively than just watching videos. Courses are designed by an award-winning team from MIT, Duke, Caltech, Microsoft, Google, and more. You will find yourself learning real-life problem-solving skills instead of memorizing equations. Brilliant can also be easily incorporated into your daily activities. with fun lessons you can do on your phone, tablet, or computer in just minutes a day. Check out their new course library. They have lessons on large language models. You can learn hands on with real language models. They can even show you the importance of training data by comparing models trained on Taylor Swift lyrics to models trained on a cookbook. But we're scientists here, so don't take my word for it. You should test it for yourself. Treat yourself to a unique hands-on experience by going to brilliant.org/michaelpenn for a 30-day free trial and 20% off your annual subscription. Thanks once again to Brilliant for sponsoring today's video.
Okay, so now that we've got a set theoretic model of n, which I've recalled right here, I replaced our successor function with just, the add1 function, as that's really all we need from here. And we want to move this on to the integers. And now I'd like to point out that since I'm going to write down natural numbers and integers here, when I'm within the integers, I'm going to use yellow chalk just to differentiate that. Okay, so here's the idea. We would like to define the integers in a way maybe like this. It should be n cross n. So that's going to be tuples of natural numbers or ordered pairs of natural numbers modulo some sort of an equivalence relation. Okay, so how should we do that? Well, I think there's probably a bunch of different ways to do this, but what's obvious to me is perhaps that the first entry here should play the role of our positive numbers, and the second entry should be play the role of our negative numbers. But what I really mean is non-negative and non-positive, because we've got the number 0 here. Okay, so like I said, this is what makes sense. So it makes sense for perhaps 0 to be equal to the equivalence class of the ordered pair 0, 0. Well, let's maybe recall what an equivalence class is now. So this is going to be all ordered pairs m and n such that mn is equivalent to 0, 0. So since we're doing modulo and equivalence relation, well, this set is really built out of equivalence classes instead of ordered pairs. Okay, so that kind of makes sense for what 0 should be. What about 1? Well, like I said, our first entry should be giving us positive numbers. So perhaps 1, oh, I forgot my color coding already. So 0, yellow 0, which means we're within the integers. Yellow 1, which means we're inside of the integers. Perhaps that should be equal to the equivalence class of 1, 0. And then after that, perhaps positive 2, so yellow 2 within the integers, should be the equivalence class of 2, 0. And then I think you can see where the pattern's going here. So again, this first entry is giving us positive numbers. It's eating up positive numbers. And then, well, the second entry should be negative numbers. So perhaps negative 1 should be equal to the equivalence class of 0, 1, because we've got our negative number right there. And then perhaps negative 2 should be equal to the equivalence class of 0, 2, and so on and so forth. Okay, well, if this first entry is giving us positive numbers, and then this second entry is giving us negative numbers, then I think it maybe pretty quickly follows that it seems like we're going to have the following setup. So the integer m minus n, so let's write this m minus n, and this is where m and n are both bigger than or equal to 0, is probably equal to the equivalence class of m comma n. Because we've got a positive part here and we've got a negative part there. Okay, well, I think from there it probably motivates what our equivalence relation should be. So notice that we can have m minus n equal to the difference of two different natural numbers as well. Notice that 5 minus 3 is equal to 2. but then also 13 minus 11 is equal to 2. So you can take any natural number, or in fact any integer, and write it in infinitely many differences. But observe that under our observation that we have decided makes sense, this should be equal to the equivalence class of KL. Well, I think that tells us what our equivalence relation should be. So our equivalence relation, which I've called this little tilde, is defined by the following condition. So the equivalence class of Mn is equal to the equivalence class of KL if and only if, well, let's recall that just based off of standard results for equivalence relations, that's if and only if M comma N is equivalent to K comma L with this equivalence relation, if and only if M minus N is equal to K minus L. And actually, perhaps this should be occurring over here in the integers. But since we don't really have integers yet, that's not really the way to look at it, because we don't know about taking the difference of integers, so we should probably move some things around so we're dealing only in the world of natural numbers. And we can do that by saying K plus N is equal to L plus M. That maybe is a translation of what we had into something that is most definitely happening inside of the natural numbers, given that K, L, M, and N are all inside of natural numbers. Okay, so there we have it. We have our set N cross N, and we have our equivalence relation, this tilde. But now we'd like to define an addition and a multiplication. So let's maybe see how this addition should be defined, and then we'll see how also the multiplication should be defined. And then, well, we have to check that those are actually correct definitions or workable definitions based off the fact that we're working with equivalence classes. Okay, so let's define addition first. Okay, so we're going to start with the equivalence class of K comma L, and then the equivalence class of M comma N, and we'd like to determine what that sum should be. But let's maybe transpose this to our world of integers, or the way that we want to think about it in terms of K minus L and M minus N. So observe that this is K minus L plus M minus N. But then we can put this back together to K plus M minus L plus N. Just, by simple arithmetic rules. But now we've got a number minus a number. Well, that's equal to an equivalence class based off of our assignment that we have. And that equivalence class is K plus M, comma L plus N. Okay, so that's how we're defining our addition. But actually, that's a pretty nice definition because we're just adding straight across these components. Okay, so now let's see what makes sense for our definition of multiplication. And we'll do this with the same game. So let's start with our equivalence class of K and L, and we're going to multiply that into the equivalence class of M and N. But let's push this down into our integer world, which we're not totally done constructing yet, but we know how it should work. And this should look like K minus L times M minus N. But now if you multiply everything out and combine the positive stuff and the negative stuff, you get the following object. You get Km plus Ln, and then minus, let's see, Lm plus Kn. Okay, well now we've got a natural number minus a natural number. That gives us a clear idea of what we should have for this multiplication. So let's put that here. We've got this multiplication is the ordered pair, or the equivalence class of the ordered pair, Km plus Ln, comma, Kn plus Lm. Okay, nice. So there we've got it. We've got our addition, we've got our multiplication, we've got our equivalence class, we've got our underlying set. Now we just have to check that all of this works, starting by showing that these two operations are well defined. So following our nose, we came up with the following nice definition or model of the integers as equivalence classes of ordered pairs of natural numbers. So that equivalence class was defined as follows. So we've got the ordered pair KL is equivalent to the ordered pair MN if and only if K plus N is equal to L plus M. Furthermore, we defined an addition and a multiplication on these equivalence classes of ordered pairs that made sense. But now, before checking that this addition and multiplication is well defined, what I'd like to do is take a step back and recall our original goal, which was to construct everything out of the empty set. So recall that we've got this set theoretic model of natural numbers, and since each of these are natural numbers, well, that's our key to doing this. That being said, we're going to need the definition of an ordered pair in terms of set theory, which is as follows. So the ordered pair xy is defined to be the set containing x and the set containing xy. And you can check that this gives you a unique or maybe a full definition of what you would want to be the ordered pair. Okay, so now let's look at the set version of the number 0 in the integers. So I've written it in yellow because we know that that's inside of the integers. So that's the equivalence class of the ordered pair 0, 0. But let's recall that 0, 0 is equivalent to everything of the form n based off of this equivalence relation. And an equivalence class is built up of everything that's equivalent to the equivalence class representative. So that means inside of this equivalence class is 0, 0 itself, 1, 1, 2, 2, 3, 3, and so on and so forth. So in other words, this is all ordered pairs n as n ranges through all natural numbers. Okay, but now what we can do is rewrite each of these as sets. So this is going to be equal to the set containing n and the set containing n. Look at that. That's just based off of our definition of ordered pairs as n runs through all natural numbers. But now each natural number is defined to be a set based off the setup that we did earlier. So perhaps we could write out a couple of these, although it gets pretty taxing pretty quickly. So let's see, we have the set containing, well, 0, 0, but what that'll be is, let's see, it'll be the set containing the empty set and the set containing the empty set. So that is the ordered pair 0, 0 based off of this definition here. So let's do a little bit of color coding to see where this is coming from. So this is this. And then let's look at 1. So 1, recall that 1 is the set containing the empty set. So this is in fact the set containing there, the empty set, and then the set containing the empty set and, well, maybe two compositions of the set containing the empty set. So we've got something that looks like that. So I think you can see how tiresome that this gets pretty quickly. But that being said, since we've already defined each natural number out of the empty set and, doing careful unions, well, we have each of these is built out of solely the empty set. Okay, so now that we've got that, let's move on to showing that these two operations are well defined. So we'll start by showing that addition is well defined. So that means we need an equivalence class with two different representatives. So let's suppose we've got the equivalence class AB is equal to the equivalence class of XY. So let's recall that that's if and only if a plus y is equal to b plus x, based off of this over here. And then we need another one as well. Let's say we've got the equivalence class of CD is equal to the equivalence class of ZW. And so again, that'll be equivalent to C plus W is equal to D plus Z. Okay, great. But now let's look at this. We've got now the equivalence class of AB plus the equivalence class of CD is equal to the equivalence class of A plus C, comma, B plus D, based off of our definition of addition. But now let's also observe that we can add these two equations to give us a new, maybe more helpful equation, that A plus C plus Y plus W is equal to B plus D plus X plus Z. But that equation tells us that the equivalence class A plus C, B plus D is equal to the equivalence class X plus Z, Y plus W, which is equal to the equivalence class of XY plus the equivalence class of ZW. Okay, so now how we really want to read this is from the extreme left to the extreme right. And what that shows is that this way that we've defined addition is in fact independent of the equivalence class representative as needed. Okay, let's move on to multiplication. Now we're moving on to showing that our multiplication inside of our integers is in fact well defined. So we'll start with the same kind of setup. We've got two equivalence classes that are equal, so they've got different equivalence class representatives. We've got two sets of those, and we want to show that we can take the product with any of the representatives we want. So what I've started with is I've started with kind of our defining property of that equality, and then I've forged those equations into four more equations. So everything in the blue box is gained by multiplying the first equation by C and then the first equation by D. And everything in the yellow box is formed by taking the second equation and multiplying by X and then by Y. Then next up, what you can do is add these two equations in the blue box. Maybe what you'll want to do is flip the order of equality, and then we'll also add the equations in the yellow box. And then after that, you can maybe build this big equation by adding the yellow component and the blue component together. I'm not going to work through all of the details. I think it'd be a nice homework exercise. And then cancel some stuff out, and you will end with the following equation. You'll end with the equation AC plus BD plus XW plus YZ is in fact equal to AD plus BC plus XZ plus YW. But what is that equation really telling us? Well, in fact, that equation is exactly what we need for this multiplication to be well defined. So that equation tells us that the equivalence class of AC plus BD, comma, AD plus BC is in fact equal to the equivalence class of XZ plus YW, comma, XW plus YZ. Oh, but this left-hand side is exactly what we defined to be A comma B times C comma D, whereas this right-hand side is exactly what we defined to be X comma Y times Z comma W. But that's all we really needed to show that this multiplication is independent of equivalence class representative, meaning that this multiplication is well defined. Okay, so there we have it. We've got a set theoretic model of the natural numbers, which we built into a model of the integers starting with just the empty set. So that means we at least have the integers built out of only the empty set. Now let's sketch how we can build the rational numbers out of the integers. Thus, the rational numbers will be completely constructed simply from the empty set. Now, from the integers, we can build the rational numbers. And we, in fact, did this earlier on the channel, so we're not going to go through all the details. So what you do is you take the set, which is the integers cross the positive integers, and you mod that out with an equivalence relation. And I've made that equivalence relation maybe an angular tilde. And what's our equivalence relation say? It says that the ordered pair AB is equivalent to the ordered pair CD if and only if AD equals BC. And this makes sense because the fraction A over B is equal to the fraction C over D if and only if AD is equal to BC. Notice we get that just from cross multiplying. Now, how should addition and multiplication be defined here? Well, let's think this. We know if we were to add the fraction A over B plus C over D, we should get the fraction AD plus BC over BD. So there we just made a common denominator. So, well, what does that mean? Well, that means if we take the equivalence class, I should be using yellow here because we're within the integers. So if we take the equivalence class of AB and we add it to the equivalence class of CD, we should get, let's see, the equivalence class of AD plus BC, comma, BD. Just because that first entry is playing the role of the numerator and the second the role of the denominator. And then, well, I'll let you write down what you need for multiplication. That's actually easier in this case. Okay, so let's see what we've done here. So we started with the empty set, and simply starting with the empty set and, well, some set theory axioms, we were able to build the complete model of the natural numbers with its arithmetic. We didn't talk about multiplication, but we'll do that in a forthcoming video. And then from the natural numbers and some tools from set theory like equivalence classes and equivalence relations, we were able to build the integers. And then again, from the integers, from this sketch right here, which like I said, we did in a previous video, we could build the rational numbers. So this is in fact what we did today. But now from the rational numbers, what you can do is use a couple of different methods to get the real numbers. So we're not going to do that today. That's actually probably best saved for a whole video on its own. And then from the real numbers, you could construct the complex numbers. And in fact, we've got a previous video where we constructed the complex numbers out of the real numbers. And in fact, you can use that method to go beyond to the quaternions, the octonions, and so on and so forth. But that being said, stopping at the complex numbers is an obvious place to stop because stuff breaks down after that. Okay, so let's see what we've got here. Barring this gap here, which we'll perhaps fill in a forthcoming video, we've shown the methods for starting at simply the empty set and arriving at the set of all complex numbers. Okay, so since you liked this video, I've got another video where I go into the Peano axioms in depth and prove the associativity and the commutativity of addition. That should be on the screen right now, and that's a good place to stop.